Antidifferentiation and indefinite integrals. Let's begin with a quick review of the fundamental theorem of calculus. Given a continuous function f, the function capital phi defined by phi of x equal to the integral from a to x of f of s ds is an antiderivative of f. That is, the derivative of phi is equal to f. If capital F is any antiderivative of little f, that is, if the derivative of capital F is little f, then capital F and phi have the same derivative, and therefore the derivative of their difference is equal to 0. So their difference is constant, and it turns out that the value of that constant is minus capital F of a, and so we have capital phi of x equal to capital F of x minus f of a. Notice that both sides of this equation have the same derivative, that's little f of x, and both sides of the equation have the same value at x equal to a, that value being 0. And therefore, the value of phi at b, the integral from a to b of f of s ds, is the same as capital F of b minus capital F of a. So we have a method for computing the integral from a to b of f of s ds. First, find an antiderivative capital F of little f, and then compute capital F of b minus capital F of a. Of course, the second step here is quite easy, provided we can do the first step. So it's that problem that we want to concentrate on here. How do we go about finding an antiderivative of a given function f? Let's start with a few important facts about antiderivatives. First, if capital F is an antiderivative of little f, then so is that function plus any constant c. This is simply because the derivative of a constant function is 0. For example, let f of x equal 3x squared. It's easy to recognize that this is the derivative of x cubed. So one antiderivative is capital F of x equals x cubed. But so is x cubed plus 1. Its derivative is also 3x squared. So is x cubed minus 5. And so is x cubed plus c for any number c. Now recall that one consequence of the mean value theorem is that if f prime of x is equal to 0 for all x in some interval, then f of x must be constant on that interval. From that it follows that if two functions have the same derivative on an interval, then those functions must differ by a constant on that interval. In other words, any two antiderivatives of little f on an interval differ by a constant on that interval. So if capital F is an antiderivative of little f, then so is capital F plus c for any constant c, and every antiderivative has that form. Example, again consider f of x equals 3x squared. One antiderivative is capital F of x equals x cubed, and therefore every antiderivative has the form x cubed plus c for some number c. The indefinite integral. Given one antiderivative capital F of little f, the expression capital F of x plus c, where c represents an arbitrary constant, provides a description of all antiderivatives of little f. This description of all antiderivatives of little f is the indefinite integral of little f, which is commonly denoted by the same symbol as the definite integral, but without limits of integration. So, given any one antiderivative capital F of little f, we write the indefinite integral of f of x dx equals capital F of x plus c. A few simple examples. First, the constant function 3 is the derivative of 3 times x. Therefore, the indefinite integral of 3 dx equals 3x plus the arbitrary constant c. The function 2x is the derivative of x squared, so the indefinite integral of 2x dx is x squared plus the arbitrary constant c. Cosine x is the derivative of sine x, so sine x is an antiderivative of cosine x, and so the indefinite integral of cosine x dx is sine x plus c. We recognize 1 over 2 times the square root of x as being the derivative of the square root of x, and so the indefinite integral of 1 over 2 square root of x dx is just the square root of x plus c. Let's now look at analogous statements about differentiation, indefinite integration, and definite integration for a few different functions. First, we know, for instance, that the derivative with respect to x of x cubed is equal to 3x squared. An equivalent statement is that the indefinite integral of 3x squared dx is equal to x cubed plus c. Now, knowing that x cubed is an antiderivative of 3x squared, we can evaluate a definite integral, such as the integral from 0 to 2 of 3x squared dx, by evaluating that antiderivative between the endpoints 0 and 2, and here we end up with 2 cubed minus 0 cubed, or 8. We know that the derivative with respect to x of 2 times the square root of x is equal to 1 over the square root of x, so we can say that the indefinite integral of 1 over the square root of x dx is 2 times the square root of x plus c. And if we wanted to calculate the definite integral from 1 to 2 of 1 over the square root of x dx, we'd use the antiderivative 2 times the square root of x and evaluate that between 1 and 2, obtaining 2 times the square root of 2 minus 2 times the square root of 1, or 2 times the quantity square root of 2 minus 1. We know that the derivative with respect to x of cosine x is equal to minus sine x, so the derivative of minus cosine x is equal to sine x, and so the indefinite integral of sine x dx is minus cosine x plus c. If we want to compute the integral from 0 to pi of sine x dx, we use the antiderivative minus cosine x and evaluate that from 0 to pi. The value of minus cosine x at pi is plus 1. Then we subtract the value of minus cosine x at 0, which is negative 1, and we end up with a value of 2 for this integral. The derivative with respect to x of x sine x plus cosine x is equal to sine x plus x cosine x, where we've applied the product rule to the first term, then plus the derivative of cosine x, which is minus sine x, and so this derivative simplifies to just x times cosine x. This computation tells us that the indefinite integral of x times cosine x dx is x times sine x plus cosine x plus c. We can also compute a definite integral, such as the integral from 0 to pi over 2 of x cosine x dx, by evaluating the antiderivative x sine x plus cosine x between 0 and pi over 2. The value at pi over 2 is pi over 2 times the sine of pi over 2, which is pi over 2 times 1, plus the cosine of pi over 2, which is 0, minus the value at 0, which is 0 plus cosine of 0, or 1, and so we get pi over 2 minus 1 for the value of that integral. You might wonder why it is that whenever we calculate a definite integral, the antiderivative that we use is always the indefinite integral without the constant c. But what we're actually doing is simply choosing c equal to 0 in order to use the simplest possible antiderivative in the calculation. If we chose a different value of c, we would still get the same answer because the c would cancel out when we did the subtraction f of b minus f of a. It turns out that the power rule for taking derivatives can easily be reversed to obtain a rule for computing antiderivatives. Let's recall that the power rule for differentiation says that the derivative with respect to x of x to the pth power is equal to p times x to the p minus 1. In other words, to compute the derivative, we multiply by the exponent and then subtract 1 from the exponent. Now, if we do the inverse steps in the reverse order, we have a rule for finding antiderivatives. The indefinite integral of x to the pth power dx is obtained by first adding 1 to the exponent and then dividing by the new exponent. So we have 1 over p plus 1 times x to the p plus 1 plus our arbitrary constant c, of course provided that p is not equal to minus 1, because if p is minus 1, then we're dividing by 0 when we divide by p plus 1. That exceptional case is quite important, and we'll revisit that special case soon. For instance, the derivative with respect to x of x cubed is 3 times x squared. To write down the indefinite integral of x squared dx, we first add 1 to the exponent, and then divide by that exponent. So we have 1/3 of x cubed, and then we add our constant c. The derivative of x to the 2/3 power is 2/3 times x to the minus 1/3. To find the indefinite integral of x to the minus 1/3 dx, we first add 1 to the power, and then divide by that new power. Now dividing by 2/3 is the same as multiplying by 3/2. And we add our constant c as usual. It turns out that the indefinite integral has exactly the same linearity properties as differentiation. Recall that we know that the derivative of f of x plus or minus g of x is the same as the sum or difference of the derivatives f prime of x plus g prime of x. Essentially working backwards, an equivalent statement is that the indefinite integral of little f of x plus or minus little g of x dx is equal to the indefinite integral of f of x dx plus or minus the indefinite integral of g of x dx, or capital F of x plus or minus capital G of x, provided those are antiderivatives of little f and g, plus the constant c. Also, the derivative with respect to x of a constant times capital F of x is the same as that constant times the derivative of capital F. This works backwards as well. The indefinite integral of a constant times little f of x dx is the same as the constant times the indefinite integral of little f of x dx, which ends up being the constant little c times any antiderivative of little f plus an arbitrary constant capital C. Notice that there's no need to multiply the arbitrary constant capital C by the specific constant little c, since little c times big C is just another arbitrary constant. Some warnings, however. We know that the derivative of a product is not the product of the derivatives, and neither is the indefinite integral of a product equal to the product of the indefinite integrals. The same thing is true about quotients. The derivative of a quotient is not the quotient of the derivatives, and the indefinite integral of a quotient is not the quotient of the indefinite integrals. Now let's look at some examples. We'll use the first one to illustrate the linearity properties in painful detail. The indefinite integral of 5x squared minus 4x plus 1 dx is equal to the indefinite integral of 5x squared dx plus the indefinite integral of minus 4x dx plus the indefinite integral of 1 dx. Next, we pull out coefficients. The indefinite integral of 5x squared dx is equal to 5 times the indefinite integral of x squared dx. The indefinite integral of minus 4x dx is equal to minus 4 times the indefinite integral of x dx. And the indefinite integral of 1 dx is just the indefinite integral of dx. Now we apply the power rule to each term. An antiderivative for x squared is 1/3 x cubed. An antiderivative for x is 1/2 x squared. And an antiderivative for 1 is just x. And then we add one arbitrary constant at the end. So simplifying, we have 5/3 x cubed minus 2x squared plus x plus c. Let's find the indefinite integral of 8x cubed minus the square root of 3x dx. The key here is how to handle the second term. We'd like to write everything in terms of powers of x, so let's rewrite the second term as minus the square root of 3 times x to the 1/2 power. So that's just a power of x times the coefficient minus the square root of 3. So now we use the power rule on each term. Antidifferentiating 8x cubed gives us 8 over 4 times x to the 4th, or 2x to the 4th. Now antidifferentiating x to the 1/2 gives us an x to the 3/2 power times a 2/3 times the minus square root of 3 coefficient that was already there. And then we add our plus c. Third, the indefinite integral of t cubed plus 1 divided by t squared dt. Here again, we'd like to express the integrand as the sum of powers of the variable. Fortunately, that's easy to do here because the denominator consists of only a single term. We just break the fraction up into two terms. The first term is t cubed over t squared, or t, and the second term is 1 over t squared, or t to the minus 2 power. Now we apply the power rule to each term, and we get 1/2 t squared, and adding 1 to the negative 2 power gives us t to the minus 1 power, and dividing by minus 1 puts a minus sign in front of that term, and finally we tack on a plus c. Now, since the function in the original problem was expressed as a single term in the form of a fraction, let's express our answer that way. The second term in our antiderivative is minus 1 over t, and so our common denominator for the first two terms should be 2 times t, and so we have t cubed minus 2 divided by 2t plus our constant c. 4. The indefinite integral of y minus 3 times the square root of y dy. Here again, we'd like to express the integrand as the sum of powers of the variable, so we multiply out the integrand and write it as y to the 3/2 power minus 3 times y to the 1/2 power. Applying the power rule to the first term gives us y to the 5/2 power divided by 5/2, which gives us 2/5 y to the 5/2. And now the second term is y to the 3/2 power times 2/3 times minus 3, so we have minus 2 times y to the 3/2, and then we add c. Now this result can be simplified by factoring. Let's factor 2/5 as well as the lowest power of y to the 3/2. That gives us a second factor of y to the first power minus 5. It's important to keep in mind that whenever we know how to take the derivative of some function capital F, we also know how to antidifferentiate its derivative. Specifically, these two statements are always equivalent. Capital F prime of x equals little f of x, and the indefinite integral of little f of x dx equals capital F of x plus c. So for every differentiation formula, we also have an antidifferentiation formula. Now let's illustrate this with the trigonometric functions. We know that the derivative of sine x is cosine x. Therefore, we know that the indefinite integral of cosine x dx is equal to sine x plus c. We know that the derivative of cosine x is minus sine x, which tells us that the derivative of minus cosine x is equal to plus sine x, and so the indefinite integral of sine x dx is equal to minus cosine x plus c. We know that the derivative with respect to x of tangent x is equal to secant squared x. Therefore, we know that the indefinite integral of secant squared x dx is equal to tangent x plus c. We know that the derivative with respect to x of secant x is secant x times tangent x, and so the indefinite integral of secant x times tangent x dx is equal to secant x plus c. The derivative of cotangent x is minus cosecant squared x, so the indefinite integral of cosecant squared x dx is equal to minus cotangent x plus c. And finally, we know that the derivative with respect to x of cosecant x is equal to minus cosecant x cotangent x, so the indefinite integral of cosecant x cotangent x dx is equal to minus cosecant x plus c. We're now going to present a few examples that illustrate a strategy that we might call guess and check. For instance, suppose we wanted to find the indefinite integral of cosine 2x dx. So we want to know an antiderivative of cosine 2x. Now, in order to obtain cosine 2x by differentiating a function, that function certainly needs to involve the sine of 2x. So let's think of that as a guess, and let's check that guess by taking its derivative. The derivative of sine 2x is equal to cosine 2x times 2 by the chain rule. So we see that we're only off by a factor of 2, or rather a factor of 1/2. In other words, if we take the derivative of 1/2 sine 2x, we will get 1 times cosine 2x. So the antiderivative that we want is 1/2 sine 2x, and the indefinite integral of cosine 2x dx is 1/2 sine 2x plus c. Another example. Suppose we want to find the indefinite integral of the square root of 3x plus 1 dx. Now, if this were a simpler problem that involved only the square root of x dx, we'd use the power rule to get x to the 3/2 power times 2/3. That suggests that an antiderivative might be something like 2/3 times the 3/2 power of 3x plus 1. Now let's check that and see how close we are. We take its derivative using the power rule followed by the chain rule, and we see that we're off by a factor of 3 there, which means that our guess at the antiderivative is off by a factor of 1/3. So an antiderivative is 1/3 times 2/3 of 3x plus 1 to the 3/2 power, and the indefinite integral is that plus c. Now this simplifies to 2/9 times 3x plus 1 to the 3/2 plus c, which we can check by taking the derivative, which ends up being the square root of 3x plus 1. Now notice that in each of these two examples, this method succeeded because our guess was really only off by a constant factor. Our next example will illustrate the limitations of this strategy. Suppose we want to find the indefinite integral of the square root of x squared plus 1 dx. Just as in the previous example, we notice that a square root arises when we take the derivative of 2/3 x to the 3/2 power, so we might guess that our antiderivative here is something like 2/3 times x squared plus 1 to the 3/2. Now let's see what happens when we take the derivative of that function. We use the power rule, which gives us 1 times x squared plus 1 to the 1/2 power, or the square root of x squared plus 1, and then the chain rule tells us to multiply by 2x. So we're off by a factor here of 2x. Now if we proceed as we did in the previous examples, we'll just divide by 2x, and hopefully that repairs our guess. So now let's check and see what happens. If you take the derivative of 1 over 3x times x squared plus 1 to the 3/2, you're going to have to use the product rule or the quotient rule, and it's going to get fairly complicated. We don't need to go through the entire calculation to notice that that is not going to be the square root of x squared plus 1. So this type of approach fails completely in this example. Now let's go back and look at all three of these examples in a slightly different light. For the indefinite integral of cosine of 2x dx, we might wish the problem were simpler, which it would be if we had a factor of 2 in the integrand, because 2 times cosine of 2x is exactly the derivative of sine of 2x. Now that's not the problem we started with. Now in order for this to be the same as the original indefinite integral, we need to multiply it by 1/2. Since 1/2 and 2 are constant factors, they can be multiplied through the integral sign to obtain a factor of 1. So now we have 1/2 of sine of 2x plus c. In the second example, the indefinite integral of the square root of 3x plus 1 dx. Now let's see if we can make adjustments here to make the problem easier. We expect to have the 3/2 power of 3x plus 1 in our antiderivative. When we take the derivative of that, we pick up a 3/2 by the power rule, as well as a 3 by the chain rule. So if our problem was to find the indefinite integral of 9/2 times the square root of 3x plus 1 dx, we're done. So all we need to do here is compensate for the 9/2 that we've introduced by putting a 2/9 outside the integral sign. So now we have 2/9 times 3x plus 1 to the 3/2 power plus c. In the third example, if we approach it the same way, we're expecting to see an x squared plus 1 to the 3/2 power in our answer. When we take the derivative of that, we pick up a 3/2 as well as a 2x. Now to compensate for that, we're going to need to put a 1 over 3x out front. So we also multiply x squared plus 1 to the 3/2 times 1 over 3x and add c. And sure enough, the second equation here is correct, but the first one is not. The problem here is that the 1 over x outside the integral does not cancel the x that's inside the integral. That sort of thing only works with constant factors. Example: Find the function f given that f prime of x equals sine of 2x plus 2 cosine 3x and f of 0 is equal to 1. The function f is going to be some antiderivative of its derivative. So let's calculate the indefinite integral so as to capture all of the antiderivatives of f prime. The sine 2x term suggests that we need a cosine of 2x, and the second term, 2 cosine 3x, suggests that we will have a sine of 3x term. The derivative of cosine of 2x is equal to minus sine of 2x times 2, so we need a minus 1/2 there so that the derivative of that term will be sine of 2x. The derivative of sine 3x is equal to 3 times the cosine of 3x, so we need a coefficient of 2/3 there, so that when we take the derivative, the coefficient will be 2. So we have a description here of every antiderivative of f prime of x. So the function we're looking for, f of x, is equal to minus 1/2 cosine of 2x plus 2/3 sine of 3x plus c for some particular c. This picture shows the graphs of several of these antiderivatives for various values of c. Notice that these curves are all parallel. Each one is just a vertical translation of any other one. We want to find a particular c so that f satisfies the additional condition f of 0 equals 1. So in other words, we're looking for the particular curve in this picture that goes through the point 0, 1. So let's see if we can find c. The requirement is that when x is equal to 0, the value of the function equals 1. So we set 1 equal to minus 1/2 cosine 0 plus 2/3 sine of 0 plus c, which says 1 equals minus 1/2 plus 0 plus c. And so we conclude that c must be 3/2. Therefore, our function is minus 1/2 cosine of 2x plus 2/3 sine of 3x plus 3/2, which we can simplify a bit by factoring out a 1/6. The other factor then is 4 times sine of 3x minus 3 times cosine of 2x plus 9. One more example. Find the area under the graph of f of x equals 1 over the square root of 5x plus 1 between x equals 0 and x equals 3. Here's the graph and the shaded region under the curve. This function is positive on that interval, so all we need to do is calculate the integral from 0 to 3 of f of x dx. Let's first find the indefinite integral of f of x. The negative 1/2 power suggests that an antiderivative should involve the positive 1/2 power. When we take the derivative of 5x plus 1 to the 1/2 power, we pick up a factor of 1/2. So let's put that factor inside the integral and compensate with a 2 on the outside. And we also get a factor of 5 by the chain rule. So let's put a 5 inside the integral and a 1/5 on the outside. So now we have 2/5 times an indefinite integral that equals 5x plus 1 to the 1/2 power plus c. So with the 2/5 factor, we have 2/5 times 5x plus 1 to the 1/2 plus c, or 2/5 of the square root of 5x plus 1 plus c. Now to compute the definite integral from 0 to 3 of f of x dx, we set c equal to 0 using the antiderivative 2/5 times the square root of 5x plus 1, and evaluate that between 0 and 3. Now this expression represents the difference of two terms, and those two terms have a common factor of 2/5, so we may as well factor out 2/5 and just evaluate the square root of 5x plus 1 between 0 and 3. Its value at 3 is the square root of 16, and its value at 0 is the square root of 1, so we have 2/5 times 4 minus 1, or 2/5 times 3, which is 6/5. So the area of that region is exactly 6/5. Now let's think about whether that's a reasonable number here. If we compare that region to this rectangle with width 3 and height 1/2, we see that the area of that rectangle is 1 1/2. So 6/5 seems to be a reasonable value for the area under the curve.